So thank you to be here. My name is Čermák, and on behalf of Professor Valášek, it's my pleasure to guide this session, which is focused on industrial production and automation department. Most of you already know that our department is divided into four groups and into two teams. The first team and his main activities are in the field of automatic control of system with time delay, and another team has the many fields, for example, the robotic applications, industrial robots, production machines, and manufacturing processes. Of course, we are solving in a lower test bed Industry 4.0. In this session, we would like to present 4 talks, and first 2 of them will be focused on the published papers in the last year, and another 2 talks, the last one, will be focused on the applied research with companies which were finalized in last year. So now I would like to give a word to the Jan Navrátil, who will talk via Zoom. So please, we will connect him. And Mr. Navrátil, please share your screen, and the floor is yours.
Hello, good morning, everyone, and welcome to my talk. My name is Saldanha, and I'm a joint PhD student at the Department of Instrumentation and Control in CACORR and at KU Leuven with Professor Wim Michels, and in CACORR with Professor Tomas Bridal. And I'll be presenting my results, which we have done in the 2 years in Leuven and in Czech, which is on stability optimization, which is applied to non-collocated vibration suppression. And this was published in the journal Mechanical Systems and Signal Processing. So, this... Is there Okay, so firstly, before I start with the main problem, let me first describe what we mean by absorption. So basically, we have a primary structure, say a building or a beam, and this structure is subject to harmonic disturbances of known frequency. So what we do is, to suppress vibrations of this non-frequency, we place a so-called absorber, and we tune the parameters of this absorber such that its resonant frequency, I'm sorry, it isn't.
Okay, so
okay, I'm sorry for the. Okay, in any case, what we do is we have a primary structure, which you see is represented by NP, and we place an absorber directly onto it, and we tune the parameters of the absorber to match the forcing frequency. And of course, we are speaking about a real absorber, so we do not have a perfect absorption. And one way to mitigate this is by using an active absorber. And one such method in the field of delays is the delay designator. But what we spoke about right now is the collocated setting. So you have a structure which is vibrating, and you can place an absorber directly onto it. In the non-collocated setting, because of practical reasons, we can't directly attach an absorber onto the part which is vibrating. And therefore, we need to place a sort of absorber remotely, as you can see in this figure. So we are targeting the mass M6 over here, and we tune the active absorber at a distant location, which is connected to M2. And so any control effort has to pass via the connected structure. And therefore, we need to take the entire structure into consideration. So one known way is to isolate the vibrating part from the resonant part by identifying a so-called resonant substructure. But this is not always possible if you have a parallel spring, for example. And with this in mind, we define our control problem. So basically, we have a system which is, in fact, our vibrating system, and we have a target which we want to cancel vibrations at, and we define our system in this way. And in addition, we also consider a non-negligible input delay, and we'll see the effect of this delay later on, and how we can also use it to our advantage, in fact. So we're using a simple control law for now, a simple output feedback. And with this, we have a closed loop system, which is defined this way. So once again, just to state our objectives is fairly simple. We want to make sure that vibrations at this target are completely suppressed. And secondly, that our overall system is stable. And we wish to maximize our stability by minimizing the so-called spectral abscissa function. And essentially, sorry. Okay, so for focusing on the vibration suppression task, we target the transmission zeros, and in terms of the stability maximization, we target the spectral abscissa function. So essentially, to explicitly target a single frequency, we assign a pair of transmission zeros on the imaginary axis, and in this way, the vibrations of this frequency are cancelled out at the output. But in doing so, we also change the dynamics of the closed loop. So we need to also make sure that our overall system is stable. And in case of our system over here, since we consider the delay as well, we must take into account that our system is infinite dimensional, and we have infinitely many characteristic roots. And secondly, in this case, we need to check only that our rightmost root lies in the left half plane to ensure that our system is stable. And we push this to the left. So in doing so, we can formulate our constraint optimization problem, which looks like this. We minimize the spectral abscissa function subject to the constraints that the zeros are located on the imaginary axis. Okay, with that in mind, we should note that this objective function is non-convex and non-smooth, and so we need to carefully use solvers to optimize our objective function. And for our task, we use elimination. So we use it specifically because the system is the objective function is non-convex, and by using elimination, we ensure that our constraints are automatically fulfilled at all locations, at all such locations. So we consider two separate cases, the single input case and the multi-input case. In the single input case, we use the property that the constraints are in general affine in the controller parameters, and that way we can eliminate the constraints and formulate the same problem as an unconstrained optimization problem. And once again, we need to keep in mind that this is non-smooth and non-convex. And for solving the resultant problem, we use two main packages. One is TDS control, which is to deal with delay systems, and secondly, Hanso, which is a solver for non-smooth optimization. And secondly, in the multi-input case, additionally, we have the constraints which are polynomial in the gain. So the elimination in this case is not fairly straightforward. But we use the property that despite it being polynomial in the gain parameters, it's still affine in a subset of the parameters. And so we perform elimination by selecting the gain parameters from a single row and expressing it as a function of the independent variables. And finally, we optimize for the independent variables. Okay, with this in mind, we move to experimentally validating our control design method, and this is our test setup in our lab. So essentially, we have a system which is excited upon by F. It's not very clear here, but it's on the right hand side, and we wish to target the mass which is at the center, using two inputs, U1 and U2, in the multi-input case, and just U1 in the single input case. Okay, so we first create a model of the system, and we apply the method which I described before. And from this, here as we see, we have the open loop poles and zeros. We see that our system is inherently stable, but the zeros are not precisely on the imaginary axis, which means that there is some kind of, these frequencies are not damped. And by parameterizing our controller using the single input case, we explicitly place the transmission zeros on the imaginary axis, and we minimize the spectral abscissa function, which you see is at around -5. So we ensure that our system is sufficiently stable. And the same for the multi-input setting as well. And with the multi-input case, we have more free parameters, so we have a better spectral abscissa. And finally, I have a small video of what this looks like. But I'm not sure. Do we have it over time?
Yes, 2 minutes.
So in the first case, we are looking at the single input setting. We have an external disturbance which is on the right hand side, F, and we're using just one actuator to suppress vibrations at the central mass. So now there is no control, and in 1 second control, and if you see the mass is completely stationary, using just a single input. And the same is also for the multi-input setting. Okay, so that was it for now. And based on the same method, we've kind of moved forward and using the same approach, we've used a single input, and we've implemented it on a dynamic delayed feedback controller to target multiple frequencies, which is in fact one of the state-of-the-art problems. And as you see in this figure, we have placed 4 zeros. We are targeting 4 frequencies, and we use the same method, but we use a delayed feedback controller. And that's it for me for now. Any questions?
Okay, thank you. One short question from audience. So, can you see any potential direct application of your model directly in the industry?
So basically our model is based on robotic manipulators, where we can't place an observer directly. So the head of a spindle, for example, and our idea is to use observers which are remote, which can be parameterized remotely to suppress it at the spindle head. But right now, I'm not working on the practical model. We are working on more of theoretical.
Okay, thank you. So, and this speak will be led by me because from this group I'm responsible for ultra-short pulse laser processing. In this case, I will present you some contract research with company which lead to a successful application. For those who don't know us, where we are in the lower test bed, we are directly in the corner. This is a booth for laser micromachining. If we look inside of this system, we can find out that it's equipped with 2 laser sources and a multi-axis kinematic, 2 Gauss scanners, cameras, etc. The most important thing is that we have 2 sources. One is short pulsed and second ultra-short pulsed, which is placed on the top of this optical board. These 2 type pulses we can combine and we can define different behavior of the interaction between material and the laser beam. If we look at this graph, there are some areas of the laser applications which correlate with the pulse duration. Looking in the micromachining applications, we have 2 areas. If we apply the same amount of energy, the average amount of energy, we can get different results, because if we shorten the pulse duration, we are getting a different maximum or peak energy, let's say. This causes that the behavior is different, and the transition between the transition energy between heat and ablation very differs. Looking at final samples created by short pulse and ultra short pulses, you can see that there is different, let's say, chip breakers fabricated on cutting inserts, and there are obvious differences in quality, surface roughness, and we are not talking about this type of machining, but it's obvious even in different type of applications. If we look at the first case where we are cooperating with many companies, for example, one company is European Cryogenics, who is creating these shafts for compounders and other things, for example, gas liquefaction. We were fabricating these grooves, which has quite big requirements on the reach depth, plus minus half micrometer, and the final roughness and the final position. Okay, we already had some technique, some technology, but the substitution by this laser micromachining was beneficial because of the system and the technological benefits, where we can get a good repeatability, productivity, and small dimensions. Another case where we are doing laser stripping or decoating of thin layers, we can apply it, for example, for manufacturers of cutting tools for example, Dormer Bramet wanted us to create some laser stripping without any affecting of the substrate material. In this picture, you can see that there were created some stairs, and there is some interface between the thin coating and the substrate without any residues of the thin layer. The final application can be done for watch industry, like this example, or the tool industry. In this case, we can have a profit from this technique, because we can do it in a selective way, in terms of that we can erase certain type of layers from the multi-layer system, or we can create only local stripping of all thickness of the layer. So that's it from my part. If you have any question, I will be glad to answer you.
So this is applied research?
Yes.
It was made for which company? I'm sorry.
The first company was the European Cryogenics, and the second one was
the volume of production.
The lower tens of pieces. But there is, in the case of this company, if we are talking about the Dormer Bramet, who is manufacturer of cutting inserts, we are talking about thousands of pieces in case of implementation of this technology. Yes?
So someone didn't get what you really did. So
we completely did this technology and developed this technology from zero to the production process, because it's not in many things it's not certain how it must be done, or how it must be the procedure. We did some optimization. We did some from let's say from the beginning, from the ablation threshold testing, to see where we can go to the with the process parameters to not avoid some subsurface structure of the material. And if you need to go to the productivity, you need to find some equilibrium in this, and that was our main contribution.
Okay, I still don't know it, but
we can talk about it later.
The next one?
Okay, I would like to invite next speaker. Mr. Chládek will tell you something about special functions of laser cutting machine control system. So, place is yours.
Thank you, Adam. Good morning, ladies and gentlemen. I'm going to present a second case of industrial cooperation, of industrial research with Czech company, Czech producer of laser cutting machines. Laser cutting, it's an industrial technology which is based on laser to vaporize material. The principle is quite simple. You need just laser source, optic path, cutting gas, and some cutting head, which is maintained in a constant distance over the cutted workpiece. On the left-hand side figure, you can see a sample of laser cutting, and you need to assure that the nozzle is within a constant distance over the cutted workpiece. The special functions which were required by the Czech producer can be summarized as follows. First, increase the cutting efficiency. It means decrease the time of cutting. And second, probably the more important, it's collision avoidance. On the left-hand side figure, you can see a sample of metal sheet in industrial production. It consists of tens or maybe hundreds of small workpieces, and and these workpieces, they are not cut in the row one after another, but the location is skipped with respect to decrease amount of the heat concentrated in the metal sheet at the time. So the machine still skips from one location to another. And on the right-hand side figure, you can see a sample of a stuck workpiece, which can cause a collision, and very often it causes a collision. So this is the motivation for special functions integration. The special functions implementation required a hardware upgrade as well. It means the proportional valve responsible for constant pressure setting, the laser source, and the most important cutting head. The new cutting head has a great benefit with a large distance control range. It enables 80 millimeters distance control compared to original only 20 millimeters range. Okay, and how does it work? So, about the increase of cutting efficiency. The efficiency is based on 3 points. First is Pierce positioning optimization. Pierce means the initial phase of cutting. You need to position the laser to initial position, start the laser, go through the cutted workpiece, and then you make the movement. And we use a distance control within this moment. On the left-hand side figure, you can see some scheme of the original and the new situation. In the original one, the laser cutting head move up in the Z direction without distance control, move in the XY plane to the target position, then move down slowly without the distance control, since the distance control range was only 20 millimeters, and then with the green arrow mark, the green arrow marks active distance controller. So we modified this procedure with as follows. We still got a distance control on and move with the direction only in XY plane, and the distance control enables the Z-axis positioning. You can modify the gradient of this movement for the user. We select a 10 scale grade, and if you select 0, you copy just the original path with the difference that the distance control is still on. It means it still checks any obstacles which are on the metal sheet. On the run hand, but there are some problems with the current installation, because there are hundreds and hundreds of G-codes which are not able to be modified at this moment. So the customers refused us to modify these G-codes. So we decided to implement our internal post-processor, which can be enabled pressing a soft key, like we call it ping pong. It simulates the movement. It's quite similar to ping pong game, you know. And if you select this functionality, this internal parser is called, it modifies the G-codes, but the user still see his original G-codes. The development, commissioning, and testing was fully performed in our laboratory in so-called lower test bed, which enables full-scale testing. It means air conditioning with filtering, commissioning, accessories, connection, and so on. You still can see this laser cutting machine at the same position like on this photo. On the right-hand side figure, you can see the active distance controller. I hope the video will go on, yeah. At this moment, the Z-axis from the controller is constant. It keeps the constant, it holds the constant position, and the movement move up and move down within the Z position. It's based on distance controller. You can find some videos when the operator puts his hand instead of a screwdriver. I was not so bothered to do that. Okay, and last point of this collaboration was implementation and the contractor, where the hardware and software was transferred to the contractor's laser cutting machine. We received 5 days to completely upgrade and update the control system and the hardware, and we did it as expected. Increase of cutting efficiency was proved, but to say how much was the efficiency changed, it's quite it's not easy because it depends on G-code. Roughly speaking, the more workpieces you cut, the higher efficiency you get, because you can skip from one cutted workpiece to another in a shorter time. And on the right hand side figure you can see a sample of the first cut workpiece, and fortunately it got stuck like that way, and this updated control system skipped over without collision. The collisions is of course very bad. It's time consuming for the operator because he had to change the nozzle, change ceramic adapter, and recalibrate this laser cutting head again. So collision avoidance was very well acknowledged. So thank you for your attention. If you've got any question, feel free to ask.